now this session about electronic measurements. In contrast to all other sessions I managed to attend in this conference, it seems like all set of authors is present, so therefore I kindly ask you to follow the agenda and not exceed 15 minutes, because otherwise we'll be late to the coffee break. So 15 minutes, I will somehow try to attract your attention if you're exceeding the time allocated for you. So about 12 minutes for presentation, and please leave like 3 minutes for questions and discussions. We will start with the presenter, Slawomir Judek, and his presentation, Wavelet transform-based approach to detect identification and railway carbon contact strips. The floor is yours.
Thank you. Good afternoon. My name is Slawomir Judek. I'm from Gdańsk University of Technology, Poland. And I would like to talk about wavelet transform-based approach to defect identification in railway carbon contact strips. Current collector is a main part of a supplying system which conduct energy to movable receiver like electric rail vehicles. Commonly, current collector is fitted with two carbon contact strips which slide along the contact wire, which is here, to provide electrical contact. So the contact strips are exposure to wear and damages, and so on. Using damaged contact strips increases the risk of the catenary rupture. So the technical condition has to be inspected frequently. It depends on overall or current collector, or especially for contact strips. Typical approach to diagnostics of current collectors is time-based preventive maintenance in rolling stock depot. Alternatively way which we prefer is new approach called condition-based maintenance, which is held on railway line, and it's based on inspection points located on the railway lines to perform diagnostic on running vehicles. Here's an example of setup which we propose for diagnostics of current collectors, especially for contact force. For diagnosis of carbon contact strips, we propose another prototype system which called laser scanning inspection system. This system was tested on the railway line. The main part of this system is 3D camera and laser line generator. The 3D camera makes some compared with laser generator, makes some measurements, and the received data have a shape of a matrix, which each number of this matrix represent height values. And we can use these values for showing it like a normal 2D image, but also we can do some visualization in 3D mode. But based on those 3D data, we propose some automatic wear estimation algorithm. This algorithm was implemented and tested, and experimental test confirmed good performance of this algorithm. However, we can also observe numerous cases of carbon contact strip defects like this. And we observed that our wear estimation algorithm is insensitive to shallow defects. So an additional algorithm is necessary for defects detections and identifications. If we take into considerations data which we have achieved from camera, we proposed an algorithm which is based off differentiation of carbon contact strips height profiles. And we expect that edges of carbon contact strips defects result in the peaks in derivative functions, and those peaks magnitudes depends on the steepness of the edges. So defect identification can be performed by finding the maximums of the derivative module and comparing with some predefined scale established afterwards based on exploitation practice. But some problems may occur because differentiation of the measured profile can be troublesome due to the low signal-to-noise ratio. It can be observed here, where we have the result of derivative obtained using difference quotients. In this situation, we have problems which peaks correspond to the damage. So differentiation method has to apply filtering and to be adjusted in such a way to enable the algorithm to accurately estimate both gentle and steep slopes. So we proposed solutions based on wavelet transport differentiation algorithm. If we look a little bit on theory of wavelet transform, we can use wavelet transform another way. Wavelet transform can be denoted as the nth-order derivative of smooth functions over a domain proportional to dilatation parameter A. So we can do two things in one way: smoothing and derivative. So to implement evaluation and validation this proposed method, we proposed standardized model of current collectors damages. This is because the shape of usual defects is highly irregular, and second reason that the calculating the reference derivative in order to obtain error of the algorithm defined as difference between the estimated and the real derivatives will be troublesome. So we proposed some co-sinusoidal defect pattern which corresponds to typical damages which we can observe in real condition. Okay? This pattern is easy to implement and easy to parameterize. Here are some results. First graph shows trapezoidal shape profile corresponding to a factory new contact strip. We add some defects in cosinusoidal shape. Here we are the same profile, but with Gaussian noise, which a level being twice of that registered by laser scanning system. Here we are our pattern derivative obtained analytically, and here we are some results, derivatives obtained using wavelet transform for different dilatation parameter A. So we can observe when dilatation parameter is increased, the smoothness of derivatives is increased too, but we lose information about values. So it's important to change proper dilatation parameter A in proper way. Also, we try to find relation between error and dilatation parameter A regards to various depths and widths of the defect. Here are some example results. here we are dilatation of Wavelet transform algorithm, which increases, and here we are an error, like a difference between ideal, theoretical derivative, and estimated through Wavelet transform algorithm. We can choose some dilatation parameter in such a way that difference between in such a way that the error of calculating of the maximum of the derivative defects is in between plus minus 50%. Additionally, the relation between error and dilatation parameter is monotonous and nonlinear. And the influence of the damage depth of the error is visible only for low values of parameter A. So to conclude, an approach to automatic carbon contact strips defects identification was proposed. The approach is based on differentiating carbon contact strips profiles and seeking the maximal and minimal derivative. Wavelet transform-based algorithm allows for differentiating noisy profiles. The filtering properties depend on a single parameter, which simplifies the process of tuning. And detections and rough evaluation of defects does not require very precise derivative estimation. However, a sensible level of uncertainty has to be ensured for a wide range of estimated slope rates. So the obtained error of value less than 50% is sufficient to meet the requirements of defects identification. Thank you very much.
Thank you for the presentation, and any questions to the presenter?
Oh, yeah, question. That's a very nice method, but I wonder if still in electrical layaway you use graphite, since that's in my knowledge nobody uses graphite.
Everyone uses.
No, I don't know. My knowledge about is Russia, and we in mine, for example, use a graphite, and graphite was destroyed very quickly.
Yes.
After 3 mines, we had to change it. Therefore, we replaced it by totally different materials. Absolutely, totally different materials.
It's correct. In European Union, there are some directives in which is described that everyone who want to ride around the Europe must use the composite graphite and carbon. Since they use from 11-12 in Poland, every railway operator use graphite.
Really?
Yes.
Maybe other questions? If it's not the case, then thank you for presentation. And well, I would like to invite the second presenter from Czech Republic, David Vala, to present his application mining shaft inspection by laser photogrammetry.
Okay, good afternoon. My name is David Vala, and I would like to present our work about the inspection of the mine shaft. It's for the introduction. We are from the Ostrava region, and maybe if you don't know where is it, it's on the northeast part of the Czech Republic. And we had a lot of mine, and it was industrial cities for the beginning, because maybe someone know, someone doesn't know where is it. So we are work generally with alternative source of energy, but one part of the energy sources in the Czech Republic is still black coal. So it's very, very important for us to, especially when mine is closed, to be able to protect and check condition of the mines, because it's very, very big problem if you take some material from the ground. It's some empty space. Okay? And finally, when you don't observe what happened inside, you don't measure the geometry of the mineshaft and so on, you can be in the problem like in the Russian, when some ground fall down and it's make a big hole in the ground. So in this case, we designed new methods for the inspection of the mining shaft based of the photogrammetry. We choose from the several methods how to measure the profile, because in fact, if you want to measure some hole, some shaft, you measure the profile of the shaft. One of the method is it's a scanning by the laser profile scanner, but it's generally designed for the line measurement, for the measurement of the profiles for the industrial application mostly. Another system for the measure of the geometry is the stereo photogrammetry. Then you use two cameras, and you need good light condition for the measurement, because to have the good contrast for the image to processing, you must find the same point of two different pictures. So it's very difficult in the mine where it's dark. Okay? So you must add a lot of light, so it's problem because you need big light sources and so on. Another task is using the single shot photogrammetry, and if you take from the dark, make the not disadvantage but advantage, because everything is dark inside. So it's easily to make the light cut plane to find the points from the one cameras, because it works on this principle, like it's line scanners, like it's in these pictures. You have the one angle of the cutting light planes and the cameras, and then you can calculate the position of each point, and it's very clearly defined where the point is. It's much more simple and faster, this algorithm for it, than using the stereo photogrammetry, because in the stereo photogrammetry we have a real two image, but in the light cutting plane single shot photogrammetry we have only the line to processing. It's much more times less data to process. So you can see the device which is used for the measurement. It's generally divided to two parts. One part is the camera system. It's you can use the high resolution camera. It doesn't matter if it's a classic still camera, digital still camera, or another type of the camera, depend of the spectral sensitivity and so on. And on the bottom part is the devising for the making the light cutting plate. It's in the first prototype we're using some system with the xenon flash and so on. It has good properties, but it's several disadvantage for the xenon light, because you need high voltage for the initial the flash, and it's a little bit danger in the mine shaft. So generally we make most advanced part in this bottom part of the measurement equipment, and it's to switch to laser system. Maybe you know the photogrammetry generally. I don't know if you're familiar or not with the system, but we're taking a picture, and then we would like to compute the properties or dimension of the shaft. It's very important, the hole distortion, because if you remove the materials, it's not only the hole to the ground, but you have many horizontal tunnels in the shaft. Yeah. So if this geometry it's not in some tolerance, it's problem, because lift in the shaft could break, or could be still inside somewhere, or it could be danger for the people and for the technology too. So from the data, from the capture data, we measure generally the whole distortion, can compute the geometry on each plane and make finally 3D models, which is on the next slide. And what is very, very interesting for us is changing and conversion during the times. It's not measure one time and never more. It's necessary to measure daily, on the daily basis, not exactly daily, by the periodical, by the week, the months, depend of how the rock massive is movement. It's depend of each location, because each location have some specific properties of the ground materials and so on. So it's not a very clear view, but if you are in the mind, it's like this. We have not many light, and only you can find a few points and must compute position. So if you would like to classic stereography, it's very big problem to find and fix the same point, because it's depend of the angle of the impact of the light to the materials and so on. It's a very big big problem to find the same point. But with the laser we can make the good cutting plate. Okay. Generally, big problem is the humidity and cold powder or some another small particle in the air, which is problem with the measurement because it's distort, and if you put the light to some small particle and reflect, so it's next problem with the optical methods. But in the single shot photogrammetry you eliminate many points because you know that it's wrong in the wrong place exactly. So it's one of our prototype. We switch from the xenon tube to the laser system. We use several laser module on the basic plane, and add some equipment like the battery, power supply, and so on to be able to light on and control the light how you need when this equipment go through the mining shaft. Okay? So one advantage is that we can control the intensity of light. We can control the duration of the flash, or it could be continuous on this laser, which is unable to do with the xenon flash. It's a lower voltage, so it's not so big problem with high voltage and intrinsic safety problems. And again, it's shock resistance because it's not very critical or mechanical critical part inside. So we base this control system on the small chip from Nordic Semiconductors with radio communication transceiver inside to communicate with the upper part with the camera, and it's like I said before, it can control the intensity, length of the flash, and another or multi-flash with the laser. It's not exactly flash because it's only the switch on, switch off the lasers. Yeah, but it's for short time we can say it's close to flash. So wireless synchronization, it's one advantage is you have no cable between two devices, so it's easily to mount it before or under the lift, and easily you can reprogram it and take data about the condition of the battery and so on. And this solution is patented in the Czech Republic. We are not patent in Europe and so on, because it's in the Europe it's more mine, it's close, so maybe in the Poland it's interesting, but we cooperate with the university in the Poland. So, and when we have data, we can compute and make reconstruction of the model of the shaft, and after reconstruction we can compare the original or projected properties and the geometry of the shaft with actual measurement, and can find some distortion and some changes during the time in the shaft. It's very interesting in the maintenance, and especially when the mine is closed, some mines must be still on, or the mining shaft, because you need taking the water from the mines to protect another mines in the region, because if you stop pumping water from the ground, it's another mines, it's flood. So it's problem in the Ostrava region, Ostrava-Karviná region, or to the Katowice, because all the ground it's interconnect between. So if on the one side of the boundary they stop pumping waters, all the mines will be flood. So it's a big problem. Okay. For the future, we work on the intrinsic safety, because probably if you know the problematic of the coal mining, it's a big problem. It's methane in coal mining. Longer battery life is it's on the working with the battery itself, and also the most effective light sources, because they have different effectivity depend of the manufacturer of the light, laser diodes and so on. Because for the really hard environment, we must little bit improve the mechanical design of all equipment, because it's a very raw industry. And also we work to real-time processing, because now it's close to offline processing. We're making the pictures, then it's go to process. In the future, we would like to be processing the online, to automatically it could be still mounted under the mine lift, and it could be on the daily basis you have actualization of the data. So it's good for the statistics and so on. I'm not geolog, so for me it's only the measurement. It must some another people to process the data and say what is wrong. Okay, it was short introduction to our problematics. Thank you for your attention.
Thank you for well-timed presentation. And we have questions.
We are just from the Institute of Mining Industry. That's very interesting things.
Okay.
Could you tell me what kind of light you use? Infrared or just visible light?
We tried using the both of them, but because the chip for the camera chip, it's a better work for us in the visible light. We're using the red laser, but we think about using the multicolor laser and have V or 3 spectral scan to be able to increase the not resolution, but recognition of the points, because sometimes it's some in the shaft it's some light sources, and so it's disturb a little bit measurement. But if we can switch it, control switch the multicolor laser or something like this. It's not exactly multicolor; it must be 3 or more lasers. Infrared laser we doesn't use now. Because it's a little bit problem to buy it with properties which we need for our experiments. But in the future, it's no problem to improve it and testing with this way.
Right. But what's the kind of data transmission? It's you use wire data. You can just already.
Already, we store it in the. We store it inside.
You take it out.
Yeah, and then I don't know where. In this upper place we store the data, and the data from the microcontroller we store inside, and then it's synchronized between, and then after it go up and remove it, we take off the memory cards and download data.
Okay.
It's not. I like say it's not real online today.
Okay.
Yeah, it's the processing. It's short, but it's.
Okay, thank you.
If there are any other questions, maybe a short question from my side about the size of data you collect. I know several people in our country working with fuel tanks, volume measurement using similar methods. They say the amount of data collected is pretty huge.
Yes.
This is the case in because shaft is longer.
Yeah, it's very long, but the resolution is vertical resolution is not per millimeters. Yeah, it's approximately in order of tens of the centimeters or up to 2 meters. Because the problem is that its mount belong the mine lift, and it had some limiting the speed of the moving. Because if you stop it, it's not good for the measurement because add some more errors. Because we compute horizontal position, vertical position from the lift today. We can add another pressure sensor and so on, but it's today we using this position. When you have the lift and if you stop it, it has some dynamical change of the rope of the cable where is the lift mount, and it's add more errors. So the best way is to go continuously down and making some slice of the, and then compare it and putting to the correct position. So in fact we use the standard memory card for the processing, and it's in order in gigabytes the data to the processing. But because we're using only the cutting the light, it's not, we not process all image but only the specific segment of the image, which is much more faster than compute the whole image. But today it's possible, but again, it's this one. It's beginning for the online processing, which you have not so much computing power.
Okay. Thank you. Thank you then for presentation once again. And our next presenter is Wojciech Walendziuk. His presentation is evaluation of PT 100 sensor deflection effect during strain measurement.
Good afternoon. Good afternoon. I would like to say a few words about platinum sensors. During our experiments, we have a lot of errors of temperature measurement, and we realized that errors source is deflection of the sensor during our experiments. That is why we started to examination of this effect as an experiment. So the main aim of this experiment is to examine influence of deflection of the platinum sensors on their resistance changes. So you know, platinum sensor works as a kind of resistor. Its resistance is changing caused by temperature. Yes, if the temperature increases, resistance increases. But if we apply such a sensor to a deflected elements, tank, for example, or cantilever beam, the resistance changes too. So, as you see on the bottom, we have different kinds of shapes of paths on the platinum on the ceramic background. So we examined two kinds of sensors, smaller one and bigger, in order to see what is the difference of resistance changes caused by deflection. The properties of the sensor are the same, but the shape and the sizes are different. We have built a laboratory stand in order to achieve repetitiveness of results. We have cantilever beam, a heater in order to change temperature. We have also step motor controller, micrometer, electronic micrometer with a serial interface, and of course data acquisition card and some sensors placed on the cantilever beam. How the laboratory stand was steered and controlled with the use of LabVIEW program. So we have cantilever beam of this size, step motor controller, micrometer with a serial interface, national instruments, data acquisition card. We have used four-wire connection in order to see what is the resistance. of the sensor. Of course, LabVIEW as a data acquisition program, and additionally, in order to see what is the temperature distribution on the cantilever beam, we have used thermal imaging camera. Here you can see a simple state machine. In such a way we prepared a program in order to do a measurement process as an automatic. We only apply some properties in this program, and whole process of measurement is automatic. Here you can see a panel of the steering panel. We can define, of course, a way of deflection of the cantilever beam, and we can see results. Of course, results are stored on the hard disk. We have additional panel in order to check if all the sensors are working correctly. It's an additional one tab. First of all, we have checked if the thermal distribution has a uniform style, uniform temperature distribution on the cantilever beam. Here you can see heater, and in the next slide you will see what is the temperature, if the temperature is uniform. Here you can see in a visible light what is the structure of the measurement sensors, how the sensors are placed. Here we can see maybe more. We have placed small one, platinum sensor, bigger one, thermocouple sensor, in order to check temperature. Of course, we can see here, maybe not see, we can have here a heater, and additionally over there is a place strain gauge sensor. Strain gauge sensor is a resistance sensor which we are using to measure deflection. Of course, we can measure a strain. In order to minimize convection airflow, mass transfer effect, we have covered whole the measurement system, maybe not exactly whole, but the part of the system, by a cubical box. In such a way, there is no influence of air which are around the laboratory stand. In this slide we can see results. Maybe we cannot see results because we have exact values achieved during our measurement process. In order to see what is the difference between initial values to the other values during our measurement, we have to use a measure like that. So we have an initial value, and we calculated difference between actual value to the initial value. For a small sensor, we can see that temperature, deflection effect is not so huge. But if we look at the huge sensor B, this one, we can see that deflection has an influence on the resistance of the sensor. Of course, we can see, but the differences for different temperatures. It is caused by increases of resistance sensor for a bigger temperatures. So the coefficient of difference is bigger. Here you can see for a 20 degrees of relation in comparison to the strain gauge sensor. It was a 120 ohms sensor. As you can see, the deflection influence is quite maybe 4 times smaller than a strain gauge sensor, which is constructed for measurement strain. For a bigger temperature, 60 degrees, you can see that effect of resistance changing is quite the same like strain gauge sensor. That is why we can say that experiments show us that we have to be aware about placing of sensors. We have to place a sensor in appropriate places which are not deflected. Of course, we can use different kind of sensors, smaller one, but we have to be aware about it. We have to know that is an influence of deflection to the sensor of temperature. So, I think it's a main conclusion to this presentation. So we can discuss it more if you have any question.
Yes. Some questions to continue with this presentation.
May I have a question?
Yes, please.
I'm sorry.
Okay.
It's good to have it.
It's interesting information. But it seems that similarity to the like you measure like a strain gauge.
Yeah.
Strain gauge is also very sensitive to temperature. Therefore, he measures the strain, but also sensitive to the temperature, and you have compensate the influence of temperature. It's a similar situation, like just opposite. You measure temperature, and you have to compensate the stress. Probably you will have to apply two such a measurement probes to do that.
Oh, we have started to apply such a sensor in order to measure temperature and strain. We have applied such a kind of sensor to our circuit, which is based on double current supply. First was a strain gauge, and the other one was temperature sensor as a PT100. And in our experiments during deflection, we have a lot of errors of measurement, proper value of temperature. That is why we have started this examination. What exactly happened? And of course we can see in this picture.
No, I don't question your problem. This problem is very important. So probably you don't understand my question. The problem is that there's a serious problem. That's really, you're absolutely right. It depends on the size of this probe.
Yes.
The longer is the size, and deflection is pretty high for you. It's pretty high. It's about 12, 15 millimeters. Is pretty high deflection. That's. However, such a possibility is. My question is that this similar problem, like you measure, for example, stress, and also you have to compensate temperature.
Yes.
In this case, you measure temperature, and you have to compensate the influence of stress.
Yes. Yes.
Information is very good.
But it's opposite. Yes, you have right. Thank you.
To rephrase that discussion, you have in mind the idea how to correct when you are obvious of the problem, but you will soon come with a proposal how to correct the measurement results.
I
They
think
are still not presented here.
But it's hard to correct such a sensor because an influence of temperature is much more bigger than the strain. So you can use only smaller sensors or different kinds, but you have to watch. You have to be aware where can I place my sensor, on which part of the machine, for example.
And this is what you not always can choose freely. Perhaps the construction of the machine leaves you a single opportunity to insert that sensor.
But you can use another one, not this, not big, not huge, not. You can use smaller one or different kind.
Okay, that's clear. If there are any other questions, if no, then thank you once again. And we then could move to the next presentation by Lukasz Makowski. Low-cost laboratory stand for turbidity measurements.
Okay, thank you, Mr. Chairman, for introducing me. Ladies and gentlemen, let me share my humble experience from my pet project, which was to create a test bed for development and research in area of turbidity measurements. This is my pet project, so not my main background, not my main area of interest, which is distributed measurement systems and wireless sensor networks. But over time, when I'm working in some projects, I became interested in details, not the huge view of the designing of the system, not the software engineering, which I was doing before, but the detail. And that detail was turbidity measurement. Why turbidity? First of all, because it's one of the key parameters with which one can assess quality of clean water or the tap water or some other water. Secondly, because it's one of the few parameters that can be measured with just electrical or optoelectronic methods. Other water parameters, factors, need to be measured with some chemical sensors or chemical methods that are applicable only in laboratory, like spectrophotometry, which is not available in situ. So my set of goals, or my main goal, is to create a testbed with which I will be able to build a wireless sensor network module that is designed to measure turbidity. Of course, one may ask why to build if one can buy. Of course, there are nice and shiny devices available on the market, like this Xiangning laboratory turbidity measurement device. They are a bit costly, perhaps. 1,000 euros for one wireless sensor network node is too much, and it's rather hard to applicate it to wireless sensor network, so no fun included in this device. Another choice, which I was using myself, is in situ probe from EC. These probes are quite large. I mean, 1 meter of the tube. This is the length of this tube, which costs itself 1,000 euros more or less. Each sensors which you can see attached to the tube cost probably the same. So this is quite expensive. We used 2 such probes on one lake, and this was costly. So I started to think. Does it have to be so expensive? Could I do it properly with less money? And so that's why I became interested in these turbidity measurements. How to measure turbidity? Perhaps you are familiar with the method. It's really simple. We have a light source which illuminates a sample. The sample contains particles which affect the light. So part of the light comes directly onto the other side. It passes through the sample. It is attenuated, so if we measure this attenuated light, attenuation level indicates how much particles are in the sample. This is due to Lambert-Beer law, perhaps you know. Lambert law says that the length of the path in the sample causes the attenuation, so the longer the path, the bigger attenuation. If we have a probe like this that has a stable dimension, this has no impact, and the Beer law says that the amount of particles in the sample cause that scattering of the light. If you measure the scattered light, this is the nephelometric method. Now I'm working on turbidimetric method, so I measure the light that goes through the sample. If you don't know that turbidity is measured in nephelometric turbidity units, just for your attention, I work in the range from about 800 to close to 0 NTU, so pretty opaque to completely translucent deionized water, which is the range of the waters you can expect in natural environment. So I was able to create requirements for a new device. First of all, I had to leave my safety zone to learn something new, to think outside my previous experiences, so I needed some courage, first of all. Then a light source, preferably a laser, because lasers are fun, lasers have coherent light, lasers are easy to couple into a narrow beam. Then a tank, a cuvette, well, something better than plastic bottle. A spectrophotometric cuvette would be the best. And finally, some light detector. As you may guess, cats are the best detectors of laser spots, but we need something more reliable. I mean, some optoelectronics. So here is my layout of my laboratory stand. Main components, main parts are on the bottom. Here is optical breadboard to which a laser and a cuvette are attached, plus some additional equipment. By the fiber there is a transducer attached. Why the fiber? Because I'm thinking about about wireless node device that can work in situ. And I don't want to submerge my transducer in some lake water. I want to float it onto the surface, but measure under the surface, few meters under the surface. So I'm starting to use fiber already now. I was observing if transducer works properly with oscilloscope and multimeter, but actually the data was transferred from analog signal, voltage signal, to digital value, and then transferred wirelessly with XB link to PC, where it was further processed and where I was creating some graphs. My laser model is 660 nanometers, so visible red light. I was avoiding intentionally infrared light, first of all, because I was afraid of the infrared, of this power, like 80 milliwatts, and secondly, this is cheaper choice. The visible lasers are much cheaper. Cuvette, like this, more or less. Here is what I had to do. I had to cut corners because I had it was my pet project, so I had little budget, and I couldn't afford a proper kinematic mount for laser, which could easily dwarf my whole project. So I had to find out some other solution, and it became clear that thing that is used by amateur astronomers who also use lasers to as a finders to aim for specific star is good enough for my project. So, I mean, it requires a lot of patience and some recalibrations over the time, but it can hold laser, and with this I can aim the laser towards the fiber at the other end. Here's the view of the breadboard, cuvette in the middle. Perhaps you can see that light is actually scattering in the sample. Here are posts with pinholes and polarizers. Polarizers were used just to attenuate the light prior to enter, before it entered the sample, because 80 milliwatts for some samples was too much. At the other end, on your right side, you can see the red spot, which is entrance of the fiber. By the fiber, the signal, the light is transferred to transducer, which is on the far right. Perhaps it's a bit dark from the beamer, but here it is. The heart of the transducer is OPT101 photodiode. Maybe you are familiar with this chip because it's for a long time on the market. It's easy to use. It has large area, large sensitive area, so easy to aim the light towards this photodiode. And finally, it has embedded amplifier, so there is no need to worry about how to connect amplifier with photodiode and avoid all these strain capacitances. I created some simple device, simple board based on the OPT101, several resistors to change gain, output through the unity gain amplifier, as it should be done. There is also a possibility to change reference level, which means that ambient light should equal 0 volts at output. When laser is off, we should have 0 volts at output. But there is always some ambient light, also which also affects the photodiode, so there is a possibility to change this reference level. This is how it looks assembled in open enclosure. The green board in the middle was what I constructed, and OPT101 in the middle, some components on the other side, of course, SMT included, knobs to change gain, to change reference level. Board is attached to XB development board, which samples the value and transfers it to PC. With this, I was able to manage to create calibration curves based on 3 standard solutions which I bought from chemical company. These solutions are traceable to Polish national standard, so quite reliable, but I had to dilute them myself. So this 200 NTU I had to dilute to lower turbidities, and you can see 2 gains over here. One should be twice as much as the other, and it is so probably it works. Another sample, an example that my dilution process was probably correct, as I started with 800 NTU and 500 NTU, and these 2 curves correspond to each other on both ranges. So it means that my chemical procedures, I'm not a chemist, but my chemical procedures in diluting were correct. And conclusions. Simple turbidimeter is quite easy to build, so it shouldn't be so expensive. It should be more affordable. It should be easier to create a wireless sensor networks with many turbidimeters. For example, in rural areas where people often have their own source of water, local source of water, which usually not is as much reliable as the water sources in cities, or they are so remote from the water treatment, water conditioning, that their water might be contaminated and above the threshold of required standards. So this is what I'm trying to develop in the next few months: a probe that will be applicable in situ or into pipe. Thank you for your attention.
It's time for some questions. The audience.
They're looking at me. That's interesting word, you know. That's but I am not wrong. You try to check the transparency of this of the water, right? Transparency of what it is.
Well, we say usually transmittance.
Transmittance.
Which is corresponding to absorbance.
Yeah.
So 100% transmittance is no absorbance.
Okay.
As you can see here. We should work between 10% of transmitters up to 100.
You are based on reflected light, is that right? Scattering problem.
I'm not measuring scattered light,
Yeah.
because it would be a nephelometry, which brings a different set of problems. For example, these particles do not scatter the light in all directions,
Right.
but there are some minimas and maximas.
Right.
So I preferred to measure the light directly in the beam path to use turbidimetry.
Okay, thank you.
Small question from my side. What are the disturbing factors in your measurement? Let's say, does that depend on the temperature of the liquids?
The main problem in such measurements is calibration and reliability of the calibration samples. Even the experienced companies like Xiangning say, for example, that creating a dilution up to or less than 5 NTU is almost impossible in most of the laboratories. So the calibration procedure is the most problematic thing here.
As usual in chemical measurements, preparation of that reference material and its handling.
I'm just trying to create a device and ask someone else to calibrate it, because when it works, it can be calibrated. Of course, calibration curves can be created in some better laboratory than I have, and it will still work.
Okay, thank you. Okay, now we will have Mr. Chang from China giving a real Eastern flavor to this our Eastern European measurement session, and his presentation is fabrication of long and smooth tungsten probes for nano-manipulation.
Good afternoon. My name is Chang. I'm from China. My university is Huazhong University of Science and Technology. It's located in the middle China, Wuhan, Hubei province. You're welcome. And my presentation is including the 4 parts. First one is the introduction. Below, there is a great need for nanoscale probes. Nanoscale probes as the end effector to manipulate a nano object and a nanostructure. But the chemical atomic force microscope probe is a good choice due to its have the ultra sharp tips whose diameter could be 10 nanometers, such as this picture shows. And this one, this white line is just the broken and adhere to the substrate. But the automatic force microscope have two disadvantages for the nano manipulation. The first one is there is a fixed angle. See it from here and the tip. Between the cantilever and the tip. And the second one is the tip is the probe is easy to be broken. At the end, at the root. So the researchers want to find another probe can alternate the automatic force microscopes. The Tungsten scanning tunnel microscope probes could be alternative to this, as with its diameters of 20 nanometers and straight axis, such as this picture shows. And its smallest edge is almost 10 millimeters. And but at the tip of the probe, it's easy to be scuffed, so it is not a good choice. So many researchers in the world have found a electrochemical etching method. It's just like this chemical equation shows. The tungsten adds 2OH and 2 water. Then the tungsten wire can be become the STM tungsten probe, then like this. But the concentration gradient of the oxygen in the manuscripts just here, just like this, it can become this manuscripts, and the shading effect make the probes with sharp, important Q, have a Q, and just like see this, just 10 millimeters. So we promote a dynamic electrochemical etching method to fabricate the probe wire. How to do this? We give the tungsten wire a picking up speed when it's immersion in the cadmium solution. And the mentioned skills is stressed here, is changed. And the shading effect of these anion layers is decreased. So it's make the X point Q decreased too. And by this way, a long and smooth tungsten probe with a constant gradient could be fabricated. Just like this. And we can see during the picking up the tungsten probe have the exit point cube here is gone. And the whole probe manufacturing system, including two parts. One is the mechanical part, and another one is electric part. This picture is our real experiment system. And during the experiment, there were a sharp drop of the parameter I, and it means the fabrication is done. And how to do this? The flow chart like this. During several steps in here, we can judge if the tungsten of the electronet. If done, they will appear a sharp drop. It means the fabrication is done. There are 5 processing methods. Sorry, maybe it's 4. In the dynamic electric chemical etching method for this tungsten fabricate. This is concentration and the etching voltage, the threshold voltage, and the picking up speed, and the emission depth. The last 2, picking up speed and the emission depth, depend on each other during our experiment. So we can call it's the 4 parameters. And the several experiments were performed to investigate the relationship between the 4 process parameters and the 3 outcomes. It's the apex diameters and the aspect ratio of the probes. The other one is how long we can consume. The first one, we can see the concentration, the solution's concentration, how to influence the 3 outcomes. This chart, we can see this is the first one. We have seen 3 outcomes is apex diameters, and this is aspect ratio, and this one is consuming time. We use the 3 different lines to express the result, and we can see at the vertical lines right is the proper interval. This is the concentration. It means the optimal concentration is 2 mole per liter. The second influence is of the etching voltage. We also investigate. See from the chart, the 3 outcomes, how to be influenced by what? By the etching voltage. We found the etching voltage is between 3 watt and 8 watt is the proper interval. And the second parameters is the threshold voltage. It influences the three outcomes like this. We found this is the proper interview. It's about 380 microwatt to 400 microwatt. During this interview, we can get better outcomes. See from the had three parameters, and the last one is the picking up speed. We also do some experiment to see this, and we get the conclusion is that the optimum picking up speed range is about 2.2 micrometers per second, and 3.2 micrometers per second. This is all 4 parameters how to influence the 3 outcomes. And see from the 4 scan chart, we found this curve is changed later. Do you see this? It means what? Means the aspect ratio is something have nothing to do, seems have nothing to do with the 4 parameters. In another side is no relationship with the 4 parameters. And the other 2 opaque diameters and the consuming times are all influenced by, or another side is determined by the 4 parameters. And how to control them, you will get a good result. So far, there's not a firm-theory formula to forecast and calculate the length of the probe personally. Maybe it's the further research. And the use of the fabricated probes for the nano-manipulation is a probe was used to bend a nanowire. This picture is photographed by us during the experiment. And another tweezer constraint use 2 such probes was used to left nanowires. This is the tweezer. And we can zoom this like this. And then I can have a conclusions. In summary, a dynamic electrochemical etching system for long and smooth tungsten probe fabrication was developed, and the mechanism of the electrochemical etching probes are discussed, and 4 independent process parameters which affect the opaque diameters and the aspect ratio of the probe and the consuming time were also investigated and optimized. With this process parameter combination, the aspect ratio of the probe were more than 8, and the opaque diameter were less than 200 nanometers. It's compared with the 10 nanometers with atom ATM progress is longer, more longer than that. And thank you.
Thank you. Thank you for the presentation, which convinced me that in nanoscale we cannot talk in separate about chemistry and mechanics. They are all together. Maybe audience would like to ask a question. Then a short question from my side is, I was wondering, how do you implement that slow movement, micrometers per second, like picking up?
Picking up, just like this. This is a tweezer, you know. To control this, there's a microscope, and how to control these two tips is here. Is changed, this distance changed by the temperature. We can give the temperature high and low to control this.
So you change the temperature,
Yeah.
it transforms the object and then moves.
Yeah.
And the temperature they really can change slowly.
Yeah. You can't to use your hand.
Okay, thank you very much. I will try to conclude this session myself. By presenting our quite easy analysis of smart power sockets implementation. We are from Kaunas University of Technology, and we saw these so-called smart power sockets, or sometimes they are regarded like outlets or plugs, became a quite popular and really affordable instrument in the era of Internet of Things. And quite a lot of articles, though not very far ago, within a range of 2 or 3 years, were published, variety of implementations, and we made an attempt to give some overview as well as our investigation and our implementations. So these electronic devices are mainly aimed to conduct several tasks: to measure electrical power consumption at every point of electrical power consumption, and support remote, mainly wireless, though it could be a power line communication, control of loads on and off, and of course reading of measurement results. The fields of application of these power sockets is power monitoring and management, home automation, load control, consumption profile monitoring, and of course Internet of Things, still looking for more applications, hopefully to boost in the near future. The architecture of power socket mainly mimics the structure of ordinary electric power meter, though there are significant restrictions on the implementation, mainly about the dimensions, because that power socket we want to be as small as possible, or even better to fit it inside the wall where the wires are connected. Nowadays electronics, these small size and low power components nearly do allow, which we convinced ourselves by assembling several prototypes, to achieve this minimization of dimensions of that measurement instrument. So the power supply, wireless connectivity module, control module, which is of course nowadays small embedded microprocessor, measurement module, and load control module, which has a load connected at its output. After overviewing all these implementations and reports by some startup companies, we convinced ourselves that there are several challenges quite little addressed. and we attempt to target them in this our investigation. And the key thing, mainly these developers get involved in wireless connectivity, but they forget or underestimate the measurement issue, measurement uncertainty, and especially in the whole measurement range. If you read about these articles, you can easily find that they say the error is 1%, but they never state in which range, which is at least not correct. A lot of applications target measurement of standby powers, quite small powers, which exposed in a long period, they attribute quite significantly to the whole power consumption and finally bills of the consumer. And the energy efficiency of that socket itself, if its goal is to measure and finally save power or give a facilitation to various policies, implementation of these saving policies, so the device itself should be as efficient as possible itself, because it will be running all a long time, the whole day, and even if the load is disconnected, that measurement instrument will consume power. This issue is also quite often underestimated. We did an overview and list in this table a scenario of possible implementations, bearing in mind structural elements of the measurement, wireless connectivity and control, shown in a preview or several slides ago, power measurement, calculation, wireless connectivity and control. So in one or other manner, embedded microcontroller is involved, but to the best of our knowledge, we were unable to find a system on chip, a semiconductor chip, which implements everything in a single chip. Energy measurement, well, the programmable controller itself, and a transceiver, wireless transceiver. The combinations do exist. I'm not going to analyze in very detail this table, but the conclusion that you could easily come from this, that there is either transceiver and microcontroller, or microcontroller and so-called specialized DSP aimed for measuring power consumption. So power consumption is measured by sensing current and voltage and then processing in a digital signal processing manner. So no single chip at the moment present in the market. Hopefully it can be done by manufacturers, but not at the moment. Therefore, for the designers, there is always a challenge which parts to select for either wireless and processor, or measurement processor coupled with the ordinary processor, and connect wireless things, wireless transceiver as a separate component on the PCB board of the smart power socket. I said I will not going to talk about wireless connectivities. They are especially in the Internet of Things related literature covered a bit more in detail and diverse applications, and I allow myself to remind the current and voltage sensing in the smart socket prototypes. Mainly we have voltage sensing options like resistive divider and transformer. As for the current sensing is shunt resistor, current transformer, and recently we have quite small offers from our available chips with a very little size based on Hall effect, and they give us an opportunity to opto or galvanic isolation of power circuits from measurement circuits. Therefore, in our investigation, we selected that Hall sensor, and then it was transformed for voltage sensing. They both are connected to separate channels to analog to digital converter with the appropriate filtering and level shifting from analog preconditioning of the signals before they are sampled and discretized. Very quite often used microcontroller is MSP 430 from Texas Instruments. The active power estimation, we in this initial study target only active power, not dealing with reactive power. And the formula is quite classical, where we multiply voltage sample and the average of two adjacent current samples in order, because there is no dual analog to digital converters. There is one converter multiplexed in time, so to reduce errors. There is well known quite long ago and patented by TI formula, where we take an average of two current samples and the voltage sample, and if you come back to the analog, then current and voltage that we sample before substituting to the formula which is calculated by the processor software, we have gains of the channels, of the measurement channels from the real current and voltage. So gains. We then have voltage at the input of current and voltage channels that we sample, and the offset corresponding current and voltage, simple linear dependence. And then active power measurement uncertainty can be derived from the previous formula following the uncertainty propagation law, which is also described in the guide of uncertainty of measurement. We assume they are not correlated, voltage and current channels, and substituting previous formulas to this one, we could arrive to the last one. And active power related uncertainty is shown in this picture, where we have this is calculation results. I will later show our verification with the reference instrument, but in this step of investigation we are mainly interested in two sources of errors, like limited number of bits sampling voltage and current, and noise of whole sensor in a current measurement circuit. These are random errors. They cannot be eliminated by calibration process. Well, many others can be corrected by calibration, but noise and whole sensor noise and quantization bits, they induce random errors. This simple chart drawn by inserting various number of bits, 8, 10 and 12, which are ordinary, makes us think that increasing number of bits above 12 does not give any significant benefit, because from 8, when we move to 10, the reduction of error in the whole scale of measured powers is obvious, but when we move from 10 to 12, the improvement, it's according to theory it should be, but it's much less, and that means that from this point the dominance of whole sensor noise is dominated, that there is no reason then to go for a more resolution, so higher resolution. Options for the reduction of these errors, of course, is the increase of sampling frequency, because if we go back to that formula, we see the sum result, and in uncorrelated values are summed, so it's sort of averaging. We increase per period more samples and we average more. So the averaging procedure is a cure to reduce random errors. As well, we could increase the number of fundamental periods, like 50 Hertz period. We could accumulate more of them, and also use this like a technique to reduce random errors. Though they are for the reduction of errors, but we need to pay a price for this. Higher sampling frequency or accumulating of more and then calculating more results is subject to increased power consumption of the power socket. It's a quite often situation nowadays in the measurement field that it's not that big problem to measure more accurately, but it's about how energy efficient we can do that, especially in a battery powered equipment, and as well in this kind of equipment where the goal is to measure energy but not to consume energy. So the minimization of energy or the achievement of predefined accuracy is of key importance in today's tasks. This towards the end, the power measurement verification we did also only on the active power with the reference instrument power analyzer from Yokogawa. We first calibrate that power socket and then try to measure after the calibration results and draw errors or mismatch of the readings of that power socket and the reference instrument. The calibration was done in a single point, 6 amperes and 220 volts with RMS values, and we see from the picture that whenever we move to a lower range of powers, the error increases, and it's about 100 watts or even 50 watts. We have quite a significant error, which is not the case in a higher power consumption region. We are nearly sure that this is because of the calibration procedure where we look only for gain factor, especially because it is quite difficult to stimulate 200 volts is okay, but if we need to derive another coefficient, at least a linear calibration, then we need a second reference point. It's not that always easy without the special transformers to have another reference point compared to 212. And this is the often approach in all the publications we have saw. Calibration is performed in one reference point, but then it means that on the edges of your measurement range you have quite significant increase of errors. Then I will finalize with the measurement errors. Several slides about power supply module, which is responsible for energy efficiency of the power socket itself. We were keen to find out if using many components of the shelf, can we at least achieve this EU eco-design directives, which asks at least or less than 0.45 watts in a standby mode of any consumer or mass production consumer device. So we made the requirements for ourselves that if a load consumes that power according to the standard, so the power socket should consume at least not more than this. It's less than this power. And we were indeed able to find that. Investigated several switching devices, even also AC-AC transformer, which is not favorable in when we consider size, but that power losses in a normal operation was about 100 milliwatts or a bit more with AC-AC transformer. And indeed, it is achievable with off-the-shelf components to achieve quite low power for the operation of this power socket itself. It was mainly in a listening mode, not in a sleep mode of a transceiver, but in a listening mode. Was quite below of the standby requirements by EU eco-design directives. And to conclude, I once again repeat that the wireless microcontroller or system on chip, which has everything needed to implement power sockets, still not available on the market. It's either controller and wireless part or controller with digital signal processor for power consumption, but not all three of them in a single package. Then current Hall sensor internal noise caused errors, dominated power measurement uncertainty budget when we have over 12-bit voltage and current quantization errors, and that especially in a low power range. Calibrating or finding only gain of that measurement channel of current and voltage is also causing increase of errors in low power range. For at least offset and gain should be calibrated. And switched mode power supply with power dissipation less than EU eco-design directives guided standby power is achievable using state-of-the-art of AC-DC converters. Several companies were investigated. And then thank you for listening. If you have any questions, I would be glad to answer.
I believe that there are other sources of there, like frequency estimation, because you are averaging over a certain amount of the periods, and if you assume that the frequency is 50 Hz, and if it is not, then those errors will also start.
Yeah, absolutely agree. We did not target all the, just selected several components that influence our the errors. To say about the frequency or the period measurement, or which samples do we collect for averaging, so it was that implementation was based on thresholding, but not zero crossing, but it was a 1 volt reference, which is internal in microcontroller, and when the voltage on car, I think we did this thresholding on the voltage signal. When the crosses that reference level, we start collecting samples, and when it crosses the next time, we stop collecting. That's why we select. And of course, yes, there are errors caused by this thing. Absolutely.
What was the way of estimation of uncertainty? Did you use analog to digital converter of microcontroller? In your calculations?
The calculation, it was done by calculating. We have a formula or a measurement model. We take parameters, we change like 8 bits, 10 bit, 12 bit, and calculate these uncertainties with these settings. About noise sensor, noise level of the sensor. So we actually measured that noise with the RMS meter on the real board, because it turned out quite larger compared to what was given in a specification of the sensor. Mm-hmm. So basically we have a formula. We take some parameters measured from a real prototype, some come from documentation, and then we calculate this.
Like limiting errors?
Yes. Okay, any other questions? If not, then thank you for attending and questions in this session, and then I would like to conclude this. Thank you.